March 7, 1943. Rechlin Luftwaffe Testing Center, Mecklenburg, northern Germany. Oberingenieur Karl Hoffmann pressed his eye against the modified microscope assembly, examining the interior mechanism of a device that American propaganda claimed could place a bomb in a pickle barrel from 20,000 feet. The Norden XV bombsight sat partially disassembled on his workbench, its brass gears and optical elements gleaming under the laboratory lights. Around him, 6 other engineers hunched over similar workstations, each focused on different sections of the captured device. They had been working on this project for 18 months. 18 months of measurements, calculations, failed prototypes, and increasingly desperate attempts to understand how American engineers had achieved such precision. The device before him represented something that should not have been possible according to German optical engineering principles. Yet here it was, captured from a B-17 flying fortress shot down over France, functioning exactly as American claims suggested. Hoffmann had built his reputation on precision optics. He had worked for Zeiss before the war, designing rangefinders and gun sights that represented the pinnacle of German optical technology. He understood lens grinding, prism alignment, mechanical computers, and stabilization systems better than perhaps any engineer in the Third Reich. He had examined British bomb sites, analyzed French fire control systems, and evaluated captured Soviet equipment. None of it had prepared him for Norden. The American device operated on principles that violated every assumption German engineers held about aerial bombardment accuracy. German doctrine, developed through years of combat experience in Spain and Poland, insisted that accurate bombing required dive angles exceeding 60 degrees. The Stuka dive bomber epitomized this philosophy. Steep dives allowed pilots to see their targets clearly, compensate for wind and altitude, and release ordnance from positions where errors in calculation had minimal impact. Level bombing from high altitude was considered inherently inaccurate. The mathematics were straightforward. A bomb released from 20,000 feet would fall for approximately 45 seconds before impact. During that time, wind could push the bomb hundreds of meters off course. The aircraft's forward velocity would carry the bomb forward, requiring complex calculations to determine the proper release point. Altitude measurement errors of even 50 meters would translate into significant aiming errors at impact. If you're enjoying this deep dive into the story, hit the subscribe button and let us know in the comments from where in the world you are watching from today. The Germans had concluded that achieving accuracy from level flight at high altitude was fundamentally impossible without sophisticated equipment that would be too complex, too expensive, and too fragile for combat conditions. Yet American bomber crews were achieving exactly this impossible accuracy with disturbing consistency. Intelligence reports from the Battle of Britain onward had documented American precision bombing. Initial German analysis dismissed these reports as exaggeration. When the United States Army Air Forces began operations over Europe in 1942, German observers expected to see area bombing similar to RAF night operations. Instead, they witnessed American formations attacking specific factories, rail yards, and industrial facilities in daylight with precision that shocked Luftwaffe commanders. The first intact Norden bombsight reached German hands in August 1941, recovered from a B-17C that had crashed in the North Sea during a delivery flight to Britain. The aircraft had ditched after mechanical failure, and German patrol boats reached the wreckage before British rescue forces arrived. Among the equipment recovered was the bombsight, still in its protective mount, damaged by seawater but largely intact. The device arrived at Rechlin in September 1941, wrapped in canvas, and accompanied by intelligence reports describing its supposed capabilities. Initial examination revealed construction quality that impressed German engineers immediately. The machining was precise, with tolerances measuring in thousandths of millimeters. The optical elements were flawless, ground to specifications that matched or exceeded German military standards. The mechanical computer, built from brass gears and cams, demonstrated sophisticated design, but impressive construction meant nothing if the fundamental concept was flawed. The first task was understanding what the device actually did. German engineers began by reverse engineering the mechanical relationships between various components. They measured every gear ratio, documented every cam profile, traced every mechanical linkage. The Norden Bombsight consisted of two primary assemblies. The stabilization platform maintained the optical system in a fixed orientation regardless of aircraft motion. The mechanical computer calculated the proper bomb release point based on airspeed, altitude, wind speed, and target motion. These two systems worked together, with the bombardier making continuous adjustments as the aircraft approached the target. The stabilization platform used a gyroscope to maintain orientation. This was not revolutionary. German gun sights and torpedo directors also used gyroscopes. What impressed German engineers was the precision of the stabilization. The Norden's gyroscope maintained the optical axis within 1/10 of 1 degree despite aircraft vibration, turbulence, and maneuvering. Achieving this level of stabilization required manufacturing precision that pushed the limits of mechanical engineering. The mechanical computer was even more sophisticated. It continuously solved ballistic equations, accounting for variables that changed throughout the bomb run. As the aircraft flew toward the target, the bombardier tracked the target through the optical sight. The mechanical computer measured the rate at which the target appeared to move across the field of view, using this information to calculate ground speed and wind drift. German bomb sights required the navigator to provide wind speed and direction before the bomb run. The bombardier would then make manual adjustments based on this information. The Norden eliminated this step by calculating wind effects automatically from observed target motion. This meant the bombardier needed only to keep the crosshairs centered on the target. The mechanical computer handled everything else. Understanding how it worked was one challenge. Replicating it was another matter entirely. Hoffmann's team began attempting to build their own version in January 1942. They started with the optical elements, assuming that German optical expertise would make this the easiest component to duplicate. Zeiss could produce lenses to any specification. The prisms and mirrors were straightforward to manufacture. The first prototype optical assembly was completed in March 1942. Testing revealed problems immediately. The American design used a specific optical configuration that minimized parallax errors while maximizing field of view. German engineers had used different approaches, prioritizing different characteristics. Simply copying the American optical layout produced a system that functioned but introduced distortions that degraded aiming accuracy. They tried modifying the design, applying German optical principles to improve performance. Every modification created new problems. Increasing magnification reduced field of view to unusable levels. Improving contrast reduced light transmission, making the sight unusable in poor visibility. Eliminating one distortion introduced different aberrations. By June 1942, they had built 7 different optical configurations, and none matched the American performance. The stabilization platform proved even more challenging. The gyroscope itself was manufacturable. German factories produced excellent gyroscopes for submarines, aircraft instruments, and fire control systems. But the Norden's gyroscope needed to be lighter, more precise, and more responsive than anything German industry produced. The American gyroscope spun at approximately 20,000 revolutions per minute, driven by compressed air from the aircraft's pneumatic system. German gyroscopes typically used electric motors, which were heavier and generated more vibration. Switching to compressed air drive required developing entirely new bearing designs, capable of operating at extreme speeds with minimal friction. Hoffmann's colleague Dieter Schmidt specialized in mechanical systems. He spent 4 months attempting to replicate the gyroscope assembly. His first prototype shook itself apart within 30 seconds of reaching operating speed. The second prototype ran smoothly but drifted significantly, losing its reference orientation within minutes. The third prototype achieved stable operation but required so much compressed air that it would have depleted the aircraft's pneumatic system in less than 10 minutes. The mechanical computer presented problems that seemed insurmountable. The Norden used approximately 30 precision gears, each machined to tolerances that required specialized equipment to verify. The gear ratios implemented specific mathematical relationships that solved the ballistic equations. Understanding these relationships required working backward from the physical gears to deduce the underlying mathematics. German engineers spent months on this analysis. They measured gear teeth under microscopes, calculated ratios to 5 decimal places, and built kinematic models to understand how information flowed through the mechanical computer. By August 1942, they understood the theory. Implementing it was another matter. Manufacturing gears to Norden specifications exceeded German production capabilities, not because German machine tools were inadequate, but because the Americans had apparently developed specialized manufacturing processes specifically for bombsight production. The gear teeth showed machining marks that suggested unusual cutting techniques. The brass alloy had properties that German metallurgists could not quite replicate, being simultaneously harder and more ductile than standard brass formulations. They tried using German standard brass. The gears wore too quickly, introducing backlash that degraded calculation accuracy. They tried hardening the brass through heat treatment. The material became brittle and gears cracked under load. They tried German nickel-silver alloys. The material properties were better, but the weight increased enough to affect gyroscope performance. By December 1942, Hoffmann's team had concluded that exactly replicating the Norden was impossible without access to American manufacturing specifications, specialized tooling, and material formulations that remained classified secrets. They shifted strategy, attempting instead to build a German bombsight that achieved similar performance through different means. This approach had worked before. German engineers routinely examined captured equipment, learned the underlying principles, and then designed German versions using different technical solutions. Soviet tank armor had inspired German developments without requiring exact replication. British radar had been studied, understood, and then improved using German electronic design philosophy. But the Norden proved resistant to this approach. Every alternative technical solution introduced new problems. Using electric gyroscope drive instead of compressed air increased weight and vibration. Substituting German optical designs for American configurations degraded performance. Simplifying the mechanical computer to use German standard gears reduced calculation accuracy. The fundamental problem, Hoffmann gradually realized, was not that the Norden used revolutionary principles that Germans could not understand. The problem was that the entire device represented a systems engineering approach that differed fundamentally from German practice. The Norden had been designed as an integrated system where every component was optimized to work with every other component. Changing any single element degraded overall performance. German military equipment emphasized modularity. Components were designed to be repairable in the field, using standard parts that could be manufactured by multiple suppliers. This approach made sense for most military equipment. A damaged radio could be repaired using standard vacuum tubes, a broken gun sight could be rebuilt using standard optical elements. Logistics favored standardization and interchangeability. The Norden took the opposite approach. It used custom components throughout, with parts manufactured to specifications that made field repair essentially impossible. A damaged Norden bombsight could not be repaired. It had to be replaced with a complete new unit. From a German military logistics perspective, this was absurd. Yet from an American perspective, it made sense. American industrial capacity allowed producing complete replacement units in quantities that made field repair unnecessary. American doctrine emphasized overwhelming material superiority over maintenance efficiency. If a bombsight was damaged, you installed a new one. You did not waste time trying to repair precision equipment under field conditions. This philosophical difference extended throughout the device. The Norden prioritized performance over maintainability, accuracy over simplicity, and system integration over component standardization. These priorities made sense for American industry and American military doctrine. They made less sense for Germany, which faced chronic shortages, limited manufacturing capacity, and supply lines that could not reliably deliver replacement equipment. Even if German engineers successfully replicated the Norden, German industry could not produce it in meaningful quantities. The manufacturing processes required specialized tooling, quality control beyond standard German practice, and materials that were already in short supply. Each bomb site would consume resources that could alternatively produce multiple conventional bomb sites, gun sites, or other optical equipment. Hoffmann documented these conclusions in a report submitted to Luftwaffe headquarters in January 1943. The report acknowledged that the Norden represented superior technology, achieving accuracy that German bomb sites could not match. It further acknowledged that German attempts to reverse engineer the device had failed to produce a manufacturable design. The report recommended abandoning the reverse engineering effort and instead focusing on German bombing doctrine that did not require such sophisticated equipment. The response from headquarters was predictable. The project would continue. Resources would be allocated. German engineering expertise would surely overcome these temporary obstacles. The Norden secrets would be unlocked, and German bombardiers would receive equipment matching American capabilities. Hoffmann returned to his workbench in February 1943, knowing the project was doomed but unable to simply abandon the work. He was an engineer. He solved problems. The fact that this particular problem might be unsolvable did not eliminate the obligation to try. Around him, his colleagues maintained similar attitudes. They would continue working until ordered to stop or until the evidence of impossibility became overwhelming enough that even Luftwaffe bureaucrats accepted reality. The spring of 1943 brought new developments that made the Norden project increasingly irrelevant to German military needs. Allied bombing of Germany intensified dramatically. The combined bomber offensive launched in earnest, with American formations striking by day and RAF formations attacking by night. German industrial capacity buckled under the assault. More immediately relevant to Hoffmann's work, the Luftwaffe faced catastrophic losses in the Mediterranean and on the Eastern Front. Aircraft production could not keep pace with combat losses. Pilot training programs were shortened to rush replacements to frontline units. Fuel supplies dwindled as Romanian oil fields came under attack, and German synthetic fuel production facilities were bombed repeatedly. In this context, developing a sophisticated bomb site for level bombers seemed absurd. Germany was not conducting precision daylight bombing campaigns. German bomber forces had shifted primarily to night operations, attacking cities rather than specific industrial targets. The missions Germany was flying did not require Norden-level precision. They required aircraft that could survive in increasingly hostile skies and deliver ordnance to approximate target areas. German resources needed to focus on fighter production, not bomb site development. Every engineer working on the Norden project represented talent that could be designing improved fighter aircraft, developing jet propulsion, or improving anti-aircraft systems. The opportunity cost of continuing the project escalated as Germany's strategic position deteriorated. Hoffmann understood this intellectually but struggled emotionally with abandoning the challenge. The Norden represented a technical problem that demanded a solution. Engineers were trained to overcome obstacles through analysis, creativity, and persistence. Admitting defeat felt like personal failure, even when rational analysis demonstrated that success was impossible given available resources. The project officially ended in June 1943. Hoffmann received orders reassigning him to Me-262 jet fighter development, work considered more critical to German military needs. The Norden Bombsight, still partially disassembled on his workbench, was packed into a crate and sent to a storage facility, where captured enemy equipment awaited future analysis that would never come. Looking back at 18 months of effort, Hoffmann recognized the project's futility had been apparent much earlier. German engineers had understood by mid-1942 that exact replication was impossible. They had known by late 1942 that even approximate replication exceeded German manufacturing capacity. Yet the project continued for 6 additional months, consuming resources and expertise that Germany desperately needed elsewhere. The reasons for this institutional inertia were complex. German military bureaucracy resisted admitting failure. Officers who had approved the project were reluctant to acknowledge their judgment had been wrong. Engineers maintained optimism that one more prototype might achieve breakthrough results. Everyone involved found reasons to continue rather than confront the reality that some American technology simply could not be copied within Germany's industrial and material constraints. This pattern repeated across multiple German reverse engineering efforts during the war. Captured Soviet T-34 tanks inspired German designs, but could not be directly copied due to German metallurgical limitations. British radar technology was analysed extensively, but the German electronics industry could not match British miniaturization. American automotive mass production techniques were documented in detail, but remained beyond German industrial capability to implement. The common thread was that successful military technology depended not just on clever design, but on entire industrial ecosystems capable of manufacturing, supplying, and supporting sophisticated equipment. The Norden Bombsight worked because American industry could produce precision brass alloys, machine gears to extreme tolerances, grind optical elements to perfect specifications, and manufacture gyroscopes with bearing surfaces smooth enough to support 20,000 RPM operation. Germany lacked some of these capabilities entirely. Other capabilities existed but were already fully committed to existing production programs. Diverting resources to bombsight production meant reducing output of other equipment. In an environment of chronic shortages and desperate military need, such trade-offs were untenable. The Norden project also revealed a more fundamental problem with German technological development during the war. German engineering culture emphasized perfectionism and sophisticated design. German engineers took pride in creating elegant solutions that demonstrated technical mastery. This approach produced exceptional individual designs, from the Tiger tank to the Me-262 jet fighter to the Type XXI submarine. But perfectionism consumed time and resources that Germany could not afford. The Tiger tank was technically superior to any Allied tank when introduced, but Germany could build only a few hundred over multiple years. The Me-262 was a revolutionary aircraft, but it arrived too late and in too few numbers to affect the air war. The Type XXI submarine incorporated advanced features that made it nearly undetectable, but only a handful became operational before Germany's surrender. American engineering philosophy prioritized adequate performance, achieved quickly, and produced in overwhelming numbers. The Sherman tank was inferior to the Tiger in direct combat, but America built 50,000 Shermans compared to Germany's 1,300 Tigers. The P-51 Mustang was not as advanced as German jet fighters, but it was available in 1944 in numbers that overwhelmed the Luftwaffe. The Norden bombsight was sophisticated, but American industry produced enough units that every heavy bomber received one, with spares available for replacements. This fundamental difference in engineering philosophy and industrial capability determined the war's outcome as surely as any battle. Germany could design superb equipment, but could not produce it fast enough or in sufficient quantity. America designed adequate equipment and produced it in quantities that made German advantages irrelevant. If you find this story engaging, please take a moment to subscribe and enable notifications. It helps us continue producing in-depth content like this. Hoffmann's experience with the Norden bombsight epitomized this disparity. He and his colleagues possessed the theoretical knowledge to understand American precision bombing technology. They had the engineering skills to analyze captured equipment and deduce underlying principles. They even had the technical creativity to envision German alternatives that might achieve similar performance through different means. What they lacked was the industrial infrastructure, material resources, and manufacturing capacity to implement their designs. Knowledge and skill meant nothing without the factories, raw materials, and production processes required to transform concepts into functional equipment. Germany was fighting an industrial war with inadequate industrial capacity, and no amount of engineering brilliance could overcome that fundamental disadvantage. The Norden project's failure foreshadowed Germany's eventual defeat. As the war progressed, similar stories repeated across every technical domain. German engineers designed advanced weapons that could not be manufactured in adequate numbers. German scientists developed revolutionary technologies that arrived too late to matter. German military planners devised strategies that depended on resources Germany no longer possessed. By mid-1943, when the Norden project officially ended, Germany's strategic position had deteriorated beyond recovery. The Wehrmacht had been defeated at Stalingrad. The Battle of the Atlantic was being lost to Allied convoy systems and air power. American industrial production had reached levels that made Axis combined output seem insignificant. The combined bomber offensive was systematically destroying German industrial capacity, while German air defenses proved increasingly inadequate. In this context, the failure to reverse engineer a single American bombsight was a minor footnote. Yet it symbolized something larger about the nature of industrial warfare in the 20th century. Victory depended not on superior individual technology, but on the ability to produce adequate technology in overwhelming quantities. America could build Norden bombsights faster than Germany could analyze captured examples. That simple fact encapsulated the industrial disparity that determined the war's outcome. Hoffman spent the remainder of the war working on jet aircraft development, contributing to designs that were technically impressive but produced in numbers too small to affect Germany's trajectory. He survived the war and returned to optical engineering in the post-war period, eventually joining a West German firm producing civilian camera equipment. In later years, when interviewed about his wartime work, he rarely mentioned the Norden project. It represented 18 months of frustration, achieving nothing meaningful except demonstrating that some problems could not be solved through engineering expertise alone. The memory embarrassed him professionally, highlighting failure rather than accomplishment. Yet the Norden episode taught lessons about technology, industry, and warfare that extended far beyond bombsight design. It demonstrated that sophisticated military equipment represented not just clever engineering, but entire industrial systems capable of producing, supporting, and sustaining complex technology. It showed that reverse engineering captured equipment was often impossible without replicating the enemy's industrial infrastructure. It revealed that engineering culture and manufacturing philosophy could be as important as technical specifications in determining what could actually be built and fielded. Most fundamentally, the Norden project illustrated the limits of technical excellence when confronted with industrial inadequacy. German engineers were among the best in the world, trained at institutions that emphasized rigorous mathematics and precise methodology. They possessed theoretical knowledge comparable to their American counterparts. Yet knowledge alone could not overcome the material and industrial constraints that limited what German industry could actually produce. The Norden bombsight sat in American bomber noses by the thousands, enabling precision attacks that systematically dismantled German industrial capacity. Hoffman's attempted copy sat in a storage crate, never progressing beyond the prototype stage, demonstrating only that some American technology remained beyond German capability to replicate. This disparity between American industrial achievement and German industrial limitation defined the war as completely as any tactical decision or strategic choice. When Hoffman examined Norden in September 1941, he saw a technical challenge that demanded a solution. By March 1943, he understood it represented something more fundamental: physical evidence that American industrial capacity exceeded German capability to such a degree that even understanding American technology was insufficient. Germany could analyze American equipment, comprehend its principles, and design theoretical alternatives. But Germany could not manufacture those alternatives in quantities that mattered, using materials that were increasingly unavailable, with industrial processes that diverted resources from more urgent needs. The 18 months spent attempting to reverse engineer the Norden Bombsight achieved nothing except demonstrating this uncomfortable reality. German engineering expertise, so celebrated and so justly respected, could not overcome the simple arithmetic of industrial warfare. America could build more, build faster, and build equipment sophisticated enough that German attempts at replication failed, even when German engineers understood exactly how the equipment functioned. This was the lesson that Hoffmann learned, staring at those precision brass gears and flawless optical elements in the spring of 1943. Technical sophistication meant nothing without industrial capacity to support it. Engineering excellence could not compensate for material shortages and manufacturing limitations. Knowledge was worthless when you lacked the means to implement it. The Norden Bombsight was not reverse-engineered by Germany, because it could not be reverse-engineered given German industrial constraints. The project was not abandoned because German engineers failed to understand the technology. It was abandoned because understanding the technology was insufficient. You also needed the factories, the materials, the specialized tooling, and the industrial infrastructure to manufacture precision equipment in quantity. America possessed all of these. Germany did not. That simple fact, more than any battle or campaign, determined which side would win the war. The Norden Bombsight, placed in pickle barrels from 20,000 feet or more, likely hitting within 100 meters of the aim point, represented American industrial dominance made tangible. German engineers could examine it, measure it, analyze it, and learn from it. But they could not replicate it, could not match it, and ultimately could not defend against the bombing campaigns it enabled. 18 months of effort by some of Germany's best engineers produced nothing except documentation of failure. Failure was not personal or professional. It was systemic, reflecting industrial limitations that no amount of engineering skill could overcome. The Norden remained an American weapon, protecting its secrets not through classification or secrecy, but through dependence on manufacturing capabilities that Germany simply did not possess. Thank you for watching. For more detailed historical breakdowns, check out the other videos on your screen now, and don't forget to subscribe.